Hello, this is a lecture in assembly language for CSC 231 at Smith College. And what I'm going to do in this lecture is review all the different ways of converting numbers in different bases. I think it's an appropriate way to spend a video lecture. So we're going to go through that. Hopefully most of that is review, and that should allow you to make sure that you master well how to deal with binary, hexadecimal, and decimal number. All right, so let's get started. So this is a table that I recommend that you generate. You know how to generate by heart. It shows all the 16 different binary combinations of zeros and ones, and they're listed in order. So you see that if you were to look at these in decimal, then each number is greater than the previous one and less than the next one, and that is true as well in binary. So 0, 1, and so on. What I've listed in the middle column is the hexadecimal number, and in the last column in italics the decimal equivalent. So all these numbers on one line would be equivalent. A is equivalent to 1010, which is also equivalent to 10 decimal. All right, so let's look at decimal to binary conversion. So let's assume that I take a number here, 101001. Well, the decomposition of this, if you want to find its value in decimal, you would go as follows: 1 times 2 to the 5th power, corresponding to this digit, plus 0 times 2 to the 4th, corresponding to this digit, and so on, down to 1 times 2 to the 0th power. So that's very similar to what you would do with decimal numbers, except that in decimal the base is 10. But you see here the powers of 2 go in increasing order: 0, 1, 2, 3, and we always start at 0. And 2 to the 0 is 1, 10 to the 0 is 1, any number to the 0th power is 1. So if you expand this, you get 32 plus 8 plus 1, which is 41. Okay, so another way of computing that quickly, you start on the right and you go 1, 2, 4, 8, 16, 32, and you kind of skip the zeros. So 1, 8, 32, 32 plus 8 plus 1, 41. So that's what you get. So now if you want to go from binary to decimal, you can, we're going to go from decimal to binary. We use a very interesting property of numbers in base 2, which actually applies to numbers in other bases, but assume that I have this binary number. So here I'm mixing both binary and decimal, but I have this binary number, which we've just expanded, and I'm dividing it by 2. So this is equivalent to taking the expansion of the number, dividing it by 2. So I can distribute the divider to all of the terms, all right? And you see that it's 1 times 2 to the 5th divided by 2, and so on. And you realize that what I'm doing here is that I'm decreasing the power of 2 by 1 because I'm dividing by 2 every term. So the 2 to the 5th become 2 to the 4th, 2 to the 4th become 2 to the 3rd, and 2 to the 2 becomes 2 to the 1, 2 to the 1 becomes 2 to the 0, and this becomes a fractional number, so I'm only looking at the integer division, so this term disappears. It's less than 1. And if it's less than 1, I'm not considering it. I'm only looking at the integer result. So this is what I get. And in binary, that number is 10100. And amazingly, what you realize is that what I get here are the top bits of this number, the top digits. So I've just removed the least significant digit. So the rule is, if you have a binary number and you divide it by 2, you get rid of the least significant digit, which is actually I've done that here. So, and if you expand that, that's 16 plus 0 plus 4 plus 0 plus 0. That's 2 to the 0 plus 2 to the 1 plus 2 to the 2nd, 2 to the 3rd, 2 to the 4th, multiplied by the correct factor. 16 plus 0 plus 4. 16 corresponds to this one. 4 corresponds to this one. And the total is 20. So 41 decimal divided by 2 is 20. That's what we were expecting. And we've lost the least significant bit because I'm only interested in integer division. So I hope that makes sense. So the rule is dividing by the base extracts the least significant digit of a number. So to illustrate how we're going to be able to use this to our advantage, what I've done is that I've written a Python program, something I like to do a lot, which is give myself an excuse for writing some code. And I thought, oh, wouldn't it be nice to write a program that will illustrate how that works on numbers? So you can take a look at the program here if you want, but it's going to be easier to see it in action and see how that works. So I've written it. It is in the handout directory. The name of the program is decimal2 binary.py. You can get a copy of it. Get copy decimal2 binary.py. And if you do that, you'll get a copy in your own account. And I'm, of course, talking to CS231 students here at Smith. Otherwise, you can go back here and look at that and recreate it. So I've made a few changes to the program. I'm making it self-executable. I'm saying use the Python interpreter that you find in the environment and use that to run the program, because Python could be version 2 or version 3 depending on what is installed on your system. And because I'm printing, I'm including this line, which is very useful, which says from the future library, which is _ future _ import the print function. And what that does is that makes the print function with parentheses work the same whether you're using version 2 or version 3 of Python. So it's a very nice way of writing a program that will be agnostic to which version of Python you're using. So let's run it, and we're going to see what, so I can run it directly without specifying Python. And it's going to ask me for a number in decimal. So let's see, I'm going to use a number like 37. And it's going to show me what happens when you divide it by 2. So it says 37 is 18 times 2 plus 1. So it has actually divided 37 by 2, figured out that it was 18, and a remainder of 1. Quotient is 18, remainder was 1. So we lose a 1. So by going from 37 to 18, you see that there's a remainder of 1 that will not be included in the division. And that's going to be important for the extension. So I'm taking 18 now, which was the result, and I'm dividing it by 2 again. So that's 9 times 2 plus 0. Quotient of 9, remainder of 0. And as I'm doing that, I'm building up the binary expansion of what 37 will be like. So now I know that the last 2 bits of 37 in binary will be 0, 1. 1, because I had a 1 here when I divided 37 by 2. Okay. So that's the one that will be thrown out. If you think that I already have the binary version of 37 and I'm dividing it by 2, I'm going to throw out the least significant digit. So that's the one here. So I know the least significant bit of 37 in binary is 1. When I do a second division by 2, I know it's 0, 1. Or third division, 9 is 4 times 2 plus 1. That one here is the one that I'm going to have here. 4 is 2 times 2 plus 0. 2 is 2 times 1 plus 0. And 1 is 0 times 2 plus 1. And here is my expansion of 37. 37 is 1, 0, 0, 1, 0. 1 plus 4 plus 32. All right, hope that makes sense. So you can play with this program and look at the rules again, and you should be able to figure this out. So kind of a neat way. I think that's something that you probably want to do on your own, is whenever you have something that you're not sure about. If you can write a program, simple program. I use Python because it's more natural for me to write in Python than Java, and it's lightweight compared to Java. I write something in Python and playing with it, usually I get to understand whatever concept I'm playing with better. So in case this is a version of decimal2 binary.py where I've removed the input, so the loop doesn't stop at every iteration. It just goes through and it gives you the whole decomposition. So here I had started with 1, 2, 3, 4, 5, and it shows me the expansion in binary that it's building up as it's iterating and dividing by 2 every time. All right, how do we go from binary to decimal? Super simple, we've done it. You just expand all the bits, you multiply each bit by the power of 2 that it's associated with. Okay, so we've seen that, and so I'm not going to spend any more time on that. Binary to hex, super easy as well. You want to divide the number that you're looking at in binary into groups of 4. So here I have 1, 2, 3, 4, 5, 6, 7 bits, 7 digits. I'm going to add a leading 0. That doesn't change the value, but now that means that I have 2 groups of 4 bits. Okay, I'm going to put a little space here to divide them. I use this table that I had created that we looked at the beginning of the lecture. And I'm looking up, so 0, 1, 0, 1, 0, 1, 0, 1 is 5. So this group will correspond to 5 hexadecimal. 0, 0, 1, 0 is 2, 5, 2. So this binary pattern is 0x52. That's the number in hexadecimal. So extremely simple way of going from binary to hex. You just need to have this table, and you can draw it on a piece of paper near you or have it available. But at some point you'll know it by heart, and you won't have to draw it. So hex to binary, simple. You use the same table, and you know that each digit in hexadecimal corresponds to 4 bits. So you replace each one by a group of 4 bits. 5 is 0, 1, 0, 1, 0, 1, 0, 1. A is 1, 0, 1, 0 right here. 1, 0, 1, 0. The same thing for 1, same thing for F. F is always all ones, 4 ones. Hex to decimal. All right, we've seen that previously. You just have to remember that the base of the hexadecimal system is 16, so you can expand that the same way that we've expanded binary, but use a different base. So it's 1 times 16, the base, to the 3rd power, so 0, 1, 2, 3, 1 times 16 to the 3rd, A times 16 to the 2nd, 2 times 16 to the 1st, F times 16 to the 0. We transform all the digits into decimal, so that's 1 times 4096, A is 10, 2 is 2, F is 15. You expand all this, you get 4096 plus 2560 plus 32 plus 15, and that's the number. So hexadecimal 1A to F is 6703 decimal. All right, decimal to hex. The best is to do decimal to binary and then binary to hex, because we've just seen binary to hex. It's very easy. So instead of learning a new rule, decimal to binary, you divide by 2 and you figure out how many bits, 1 or 0, you're throwing out through the division. All right, so that's the lecture that I have prepared for you. So what I suggest you do is go to this page. I'm going to click on that. And I have prepared, so this is very good actually preparation for the midterm. So what I have are some exercises that will ask you to convert hexadecimal into various bases. So as part of the lecture, what I'd like you to do is to spend the time going through all of them and record your questions if you have any. And if you can go through all of them relatively fast and easily, then you can be sure you'll have some of these questions for the midterm, so you'll be ready for that. So short lecture on my part, but asking you to do some work to verify your knowledge. And if none of that kind of makes sense, or if you forget how to do something, I would suggest you go back through the slides and review what I've just gone through very, very quickly, very briefly, and you should be fine. Good luck.